fellow students. On behalf of all the authors, I'm glad to have this chance presenting my study in this stage. My research topic is the application of constellation shaping and artificial intelligence in underwater visible light communication, UVLC. The following content includes a brief introduction of the research background, next the principle and method used in our study, then the experiment setting and result, and finally, the conclusions of this study. So first, let's look at the background. After 5G, the communication technique is now striking into the next era, 6G. It is predicted to provide significantly more channels within less delays. At present, it is not satisfied by the current underwater communication method. The acoustic signal doesn't have enough modulation bandwidth, and RF cannot penetrate natural water environment for long distance. However, thanks to the blue-green transmission window, we can send visible light signal through a middle range in the water, and the literature has shown that visible light channel has the ability to achieve gigabits per second data rate. High-speed applications such as wireless fiber integrated system are therefore available. Another advantage is that VLC system can be implemented by LED device whose market increases in a fast-growing trend. Hence, it is a promising technique to study LED-based VLC system. A major challenge in VLC is that it is now limited by nonlinearity problem. The root of it is the intensity modulation, direct detection, or IMDD method we use in modulation, and a lack of coherent transmission. In the intensive conversion between light and electric signals, the device would cause distortion due to the nonlinear response. In this case, the constellation is distorted, showing messier peripheral points area than the central ones. Different constellation points would encounter different extent of influence from nonlinearity. For example, the APSK constellation has more distorted points than QUAM in the same modulation order. To alleviate the negative effect by nonlinearity and recover the signal, extensive studies have been done for post-equalization methods. An ideal post-equalizer could model the channel precisely and offset the channel effect from the received signal. However, due to the complexity of VLC channel, we usually apply a data-driven style solution, such as adaptive linear filter, LMS, or nonlinear filter, Volterra, and neural network. Among these solutions, LMS can only perform linear fitting, and Volterra equalizer, it has a complexity exponentially growing with its order. But neural network has a flexible and powerful fitting capability in acceptable complexity, and it can map the waveform samples directly to constellation points and merge post-equalization into demodulation. So this feature attracts us to apply it in our study. And next, we will enter the section of method. The modulation scheme used is carrierless amplitude and phase modulation, or we call it CAP. It can map the first stage symbol of arbitrary order into waveform. Hence, it can approach to the channel limit by a flexible tuning. It uses two orthogonal pulse shaping filters to merge the in-phase and quadrature signal in the same stream of real-valued waveform without an explicit carrier mixing process. Hence, it is called carrierless. It's obvious that the larger the first stage symbol, the larger the first stage symbol, the more possible the waveform output power might be. And in this study, we investigate two options, QUAM and APSK, as the first stage symbol. QUAM as a classic choice, it has gray gain, which would ensure that only one bit error would occur when the decision process choose an adjacent constellation symbol by mistake. However, it does not utilize the maximum usable power. In the peak power limited system, this means a small signal noise ratio, and in underwater environment, smaller signal power would be a weakness as this undermines the transmission range. But by contrast, although APSK does not have gray gain, it has a large average power when the peak power is limited. This suggests that it has a potential to reach longer communication range. But this has a premise that it requires a powerful tool to recover distorted constellation points at the peripheral area, or it's a mistake to use APSK rather than QAM. Well, to solve this issue, we introduce NN as a powerful post-equalization tool. As the figure shows, waveform samples are converted from serial to parallel arrangement first and next fed into the NN. Rather than using real-valued NN, we use a complex-valued one. It updates the weight parameter at the last layer using the same gradient. However, real-valued NN will first split the gradient to two and pass them either to just the weight linking to the output 1 or output 2. Here we present the comparison within the same training setting, showing that real-valued NN is trying to linearize the constellation points and cause distortion, but complex-valued NN could keep the round shape of them. So in the experiment process, we established a underwater communication environment. We use a AWG as the signal source and coupling with the driving circuit and a blue light LED to utilize the blue-green transmission window. The water tank is 1.2 meter long, filling with tap water. The signal is received by a PIN photo detector and sampled by oscilloscope. We test both 32 array and 64 array case using 3 gigabits per second and 2.9 gigabits per second data rate, respectively. We choose LMS and the second order water post equalizer as the benchmark to compare the performance of NN. Well, it performs waveform stage signal recovery, and the demodulation part is done using traditional cap demodulation process. The training result is a bit underfitting to prevent constellation distortion and overfitting result. The first comparison in 64 array is shown in this line graph. The constellation difference is significant. When using traditional LMS or Volterra post-equalization, the red line, the 64 APSK outperforms the blue line, or 64 QAM in minimum bit error rate. APSK leads QAM by 37%. When applying NN as the equalization method, APSK is enhanced more in high VPP area and outperforms QAM. In the meantime, APSK has a larger dynamic range. When choosing 3.8 E-3 as the threshold for 7% forward error coding, the BR upper bound APSK plus complex valued N has a working range of 350 millivolts, which is 150 millivolts larger than that in QAM plus conventional DSP process. The minimum BR is further lowered by 20% in APSK and 17.8% in QAM by complex valued DNN. When using the real-valued NN, this figure is slightly smaller, especially at high VPP area, showing that complex valued network is more capable for high nonlinearity. For details, we plot the ring diagram at 700 millivolts and constellation points at 3 different power levels from low to high power. In the ring diagram, well, the x-axis means the position of transmitted symbols, and y-axis means that of the received ones. 64 APSK has 4 rings in the constellation diagram, so there are 16 grid points, and 64 QAM has more rings because it's square. The color bar represents the probability. The brightest diagonal line means the most of the symbols are recovered at the same radio distance to the origin. When the signal power is low, noise is the dominating factor for BR, and the dispersion on radio distance is not symmetric due to nonlinearity. The symbol tend to appear at a position closer to the origin. We can see that the baseline has a stronger nonlinearity than the NN solution from both the ruin diagram and the constellation. In 32 array case, the line chart showing a similar trend, but due to a lower signal level, the BR level is generally higher, so the threshold is rising to 1.5 E-2, the threshold for 20% redundancy forward error correction. And when using the conventional post-equalizer APSK leads QAM by 22%. The maximum allowable BPP is extended by 50 millivolts by APSK and NN. The minimum BR is lowered by DNN by 33.7% compared with QAM in conventional solution and 15.1% for APSK in conventional solution. I mean, use LMS plus Ultra. And complex valve NN surpasses its revalve counterpart in large VPP. Well, but interestingly, the 32 APSK does not surpass QAM in either low VPP or high VPP. This phenomenon could be attributed to the atypical constellation of 32 QAM, which omits the 4 points at the corner, and hence it is not a perfect square. But still, we can find the advantage of NN in BER performance, and although this time, due to the lower SNR, NN is weakened because NN cannot deal with noise, it's yet more capable than the baseline. In the conclusion section, we will refer to the assumptions in the previous parts. And first, the APSK proves its advantage in 64 array order. The exception is that the 32 array case, because 32 QAM is not completely square shaped, it's not a typical QAM constellation. And secondly, the performance of NN is even better than the chosen baseline, showing that it's capable for the integrated function. Considering that its complexity is more than the waveform equalization, it proves the ability of NN in fitting complex nonlinear mapping. And finally, complex valid NN has a better performance in high signal power in all of the combinations. It means that the topology of network does has an influence in training efficiency, and it is recommended to use it in recovering highly distorted constellation in high nonlinearity. And this is all the content of my presentation. And thank you for your attention. Is there any questions?
Thanks, Dr. Xu. Any questions from the online audience and the on-site audience? Okay. If no question, maybe we can go ahead. Now is Dr. Zong Cheng available now? Is online? Dr. Zong?
Can you hear me?
Yes.
Oh, okay.
Yeah.
Sorry.
The next speaker will be Dr. Zong, right? His talk is on theoretical attenuation model for indoor fiber wireless